Okay, sorry for those of you who are watching. We just went over the first problem, but we'll try problem 1b right now. And they're very similar. This one, you're doing the summation from k equals 1 to n of 2k is equal to n squared plus n. So what I'm going to have you start by doing is just expand that. See if you understand what it's even saying. Expand it, just see what you get. So for the expansion, you plug in 1, and 2 times 1 is 2. Then you plug in 2, and you get 4. Plug in 3, and you get 6. Plug in 4, and you get 8. Plug in 5, and you get 10. You stop at plugging in n. And when you plug in n, you should have 2n over here. And that should produce n squared plus n. Thumbs up if you had all that on your own. Good job. Now, what you're saying is that if you add up the first even number of terms, you get this thing. So we talked about the odds, right? Turns out if you add up the first 100 even terms, so 2 plus 4 plus 6 plus dot 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 plus, let's see, if you add up, let's see, 200, that would be your 100th term. If you add those up, all you have to do is do 100 squared plus 100, which is 10,100. So I added those up that quickly. Happened rather fast, didn't it? We want to prove that that is actually true, which again, saying that to you guys isn't that big of a deal, but could you imagine trying to communicate to somebody else? You're trying to prove it works for every single integer that you can think of. They'd be like, well, that would take eternity. And you're like, no, I'm just going to use math induction. It's no big deal. So you start step number 1. Show the rule holds true for the first few cases. I want you to show case 1, case 2, and case 3. Show that it works for those 3, okay? And after that, pause, and then we'll move on to step 2. Anyway. All right, let's see what you get. Case 1, I choose the very first term. Okay, this is my first term right here. First, second, third, fourth, fifth. This is the nth term. Okay, and so my first term is 2. And that should be equal to 1 squared plus 1. See how that's written out? My first term is 2, and that was for an n value of 1. And that works. I get 2. So check that off. For case 2, I'm going to add the first 2 terms. So you should have 2 plus 4. What do we plug in for n? We plug in 2. We're at case 2. So 2 squared plus 2. And that's total 6. And then move on to the third one. 2 plus 4 plus 6. I have those first 3 terms. What do I plug in for n? You plug in that 3 because you just did 3 terms. And you can see you get 12, and that works all the way across. Are you able to do those? Good. Step 2 is the inductive hypothesis step. See if you can write it out correctly. Take about 45 seconds, and then we'll check see if you did it right. You should have written down, assume the rule holds true for case n equals k. Did have a student during first hour, they said that they would just prefer not to write that, and that's okay. I then mark it wrong on the test, okay? So this is part of your proof. You're communicating to me. And believe it or not, sometimes I wonder if you know what you're doing. You could see where I might wonder, right? So I need to see you communicate that. So it would be 2 plus 4 plus 6 plus 8 plus, you could stop at 6 or 8 or 10 or whatever. I'm just going to go dot, 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 plus, and we are going to stop at k this time. So if you plug k in, you just get 2k. And that's equal to then k squared plus k. And that is your inductive hypothesis. Any question how we came up with that? Okay, Then the third one, there was a question first hour. We'll see if you guys get it, but please write out 3, which is show the rule holds true for case n equals k plus 1. And see if you can write the expansion for what that looks like. Okay, here we go. So let's see what this expansion is. You should have 2 plus 4 plus 6 plus 8 plus dot, 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 dot. And then you should have 2k. And then instead of stopping at the k term, remember, this is our first term, second term, third term, fourth term. This is our k term. We want the k plus 1 term. So when you plug k plus 1 into this guy right there, you get 2 times the quantity k plus 1. 2 times k plus 1. And so now, instead of n terms, you have k plus 1 terms. So k plus 1 squared plus k plus 1. That was the, this is where some people were confused first hour. Is there any question how I got that piece or where I pulled it from? Okay, then you tell me what to do now. Good. I use my inductive hypothesis. This thing will always end up showing up right here. So you can see this 2 plus 4 plus 6 plus 8 all the way to 2k is exactly this thing I have right there. And we know that that's k squared plus k because we see it right there. So we get k squared plus k. And then what remains? That thing, 2 times k plus 1. And we have to get it to be that thing that's on the right. Well, that's no big deal. We can do that. Let's just combine some like terms. K squared plus, let's see, 2 times k is 2k plus k is 3k. And then 2 times 1 is 2. Now, these things do look a little bit different, don't they? They look a little bit different than this right here. But we can always look at it and see, oh, it looks like it's factored a little bit, doesn't it? So let's just go ahead and try to stretch things out a little bit. K squared plus, what does this multiply out to? K squared plus 2k plus 1, right? Plus 2k plus 1. Now, let's see here. I have 3 k's though, right? I have 3 k's, so you should have another k in there. And then 2 and 1, let's see, I should have another 1 in there, shouldn't I? So, does everybody see that all I did here was I just saw that 3k and I made it into 2k and 1k. And then I saw that 2 and I made it into 1 and 1. Is that going to help me make it look more like this? Yeah, it sure is. Because right now, this then factors to k plus 1 quantity squared plus k plus 1, which is exactly what we had, k plus 1 quantity squared plus k plus 1. QED, which is Latin for that which was to be demonstrated has now been shown. And that's a beautiful proof. You're going to see the third one as far as you can on your own with a partner or two. Okay, so you're just going to take it as far as you can. Sum from k equals 1 to n of 3k minus 2 is equal to 3n squared minus n over 2. And I'm going to come around and just kind of start checking in and see where you're at. But you want to see this as far through as you possibly can. For those listening, I'm going to start writing the proof out as people have been working on it. They're doing a very good job. those watching, I'm going to show it holds true for the first few cases. Start with case n equals 1. Well, not m. N is equal to 1. And you can see that this is my first term, my second, my third, my fourth. It's my nth term. So the first case would be 1 is equal to 3 times 1 squared minus 1 divided by 2, which is 2 over 2, which is 1. That worked. I'm going to try case n equals 2, which would be 1 plus 4. That should be equal to 3 times 2 squared minus 2 over 2. Let's see, that would be 2 squared is 4 times 3 is 12 minus 2 over 2, or 10 over 2, which is 5, and that's what 1 plus 4 is. If I try case n is equal to 3, 1 plus 4 plus 7, that should be 3 times 3 squared minus 3 over 2. 3 squared is 9, times 3 is 27, minus 3 is 24, divided by 2 is 12. And sure enough, 1 plus 4 plus 7 is 12. So I can now step to 2, which is assume the rule holds true for case n is equal to k. And for those of you who are sitting down right now in my classroom, please make sure that your step 2, make sure that it follows along with this. 1 plus 4 plus 7 plus 10 plus dot 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 plus 3 times k minus 3k minus 2 is equal to 3k squared minus k divided by 2. For those of you sitting down right now, does step 2, does that match with what you had? Okay. Then and that's my inductive hypothesis. I would like to put IH there. So number 3, then show the rule holds true for case n is equal to k plus 1. So please make sure that you have this identical. 1 plus 4 plus 7 plus 10 plus dot 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 plus 3k minus 2. So this is your first term, second term, third term, fourth term. This is your k term. I need the k plus 1 term. The k plus 1 term is 3 times k plus 1 minus 2. And that's going to be equal to 3 times k plus 1 squared minus k plus 1 all over 2. That's what we need. And this is where some of you got stuck, right? Okay, this is a lot of times where people get stuck. So that's okay. We need to show you another little trick here. So if you got this far, you're doing an excellent, excellent, excellent job. I just need to put something in for that. What do you put in for that? Excellent. 3k squared minus k all over 2. And that's by our inductive hypothesis from above. And so then we're going to add to that 3k minus 2. And that's supposed to be, I'm sorry. We're going to add to that 3 times k plus 1 minus 2. And that's supposed to be equal to 3 times k plus 1 quantity squared minus k plus 1 all over 2. So let's just do the algebra here. I'm sorry if we run out of time. Please just stick around so we can finish it off quick. But what would you do to make this left side look like the right side? What's the first thing you would do? Yeah, common denominators. So I'll multiply the top and bottom by 2. And when I say by 2, I'll multiply everything. Notice what you get. You get 3k squared minus k. And it'll be 6 times k, which is 6k. And it'll be 6 times 1, which is 6. And then 2 times negative 2, which is negative 4. And that bothers some people, but if we just gather it all together, we get 3k squared plus 5k plus 2 all over 2. Is everybody okay with that? Now, here's the part that I feel like people get really confused on it. If you just follow this one thing, it won't be bad at all. If we multiply k plus 1 squared, don't you get k squared plus 2k? plus 1. And if you multiply it by 3, you get 3k squared plus 6k plus 3. So watch what I'm going to do here. This is a trick, but it's a good trick. 3k squared plus, I don't want 5k, I want how many k's? 6k. So I'll put 6k there. Well, if I put a 6k there, then I have to put a minus k here, right? Because does a 6k and negative k make 5k? And then look here. What number do you want on the end here? You don't want 2, you want 3. So I'll put a plus 3 here, and I'll put a minus 1. Because doesn't the 3 and the negative 1 make 2? Everybody okay with that? And that's all over 2. So what should I factor out of this? A 3. And if you do, you get k squared plus 2k plus 1. What should you factor out of this? A negative 1. And you get k plus 1. Ooh, that looks pretty close to what we need, isn't it? All we have to do is just recognize that that's a perfect square. As in 3 times k plus 1 quantity squared minus k plus 1 divided by 2. And that equals 3 times k plus 1 quantity squared minus k plus 1 divided by 2. Sorry for keeping you late. Just we were kind of at that aha moment. That's a cool trick. You're really close to being ready. Tomorrow it should really wrap up for you. You're doing good work. Good job. We'll see you soon.